This conference will now be recorded.
Very good evening, student.
This conference will now be recorded.
Very good evening, students. We are discussing capacitor and capacitance in the chapter electrostatics. So we had somewhat discussed about capacitor, capacitance, its dimension units, and also how a capacitor stores energy. And you might be remembering the expression for the electrostatic potential energy stored in capacitor is U is equal to Q square by 2C, or it can be equally written as half cb square, as you know. So now in the last class also we had discussed one topic called redistribution of charges. So one small part we had not discussed in that, we'll just discuss today. So before we discuss, let me just before I discuss that particular part, I'll just recap a little bit about redistribution of charges. See here, first I have picked up an example or comparison how charge redistribution happens. See, you can see this is a container which has two arms. One is this one, which is narrow arm, and the volume of this one is actually larger. These arms are actually connected through this valve, and you can see initially this is the initial situation, figure A, initially, and this is finally what is happening. Okay, so initially the valve is closed. Okay, this is closed, and you can see this arm, left arm, is filled almost full, whereas this is filled but not completely. Now as soon as this valve is opened, what happens, you know, due to the, like, according to the properties of liquid, that, see, the pressure on this part is atmospheric pressure, since it is open to the atmosphere. Here also it is open to the atmosphere, so pressure will be same, and at same horizontal plane or same horizontal distance, pressure on the liquid surface will be the same, and hence it doesn't matter whether the volume is more here. Suppose volume is V1 here and it is V2. So even though the V2 is greater than V1, see, the liquid is actually coming down from left arm to the right arm, and this flow will continue until and unless the height in the two arms become equal. So similar thing happens, sorry, if you have two capacitors. Suppose these are two spherical capacitors, this is R1 and this is R2, have a radius. Okay, so you know the capacitance is actually directly proportional to R in case of spherical capacitor. So this has less capacitance and this has more capacitance. That means, you know, this can accumulate less charges, and this can, R2 can accumulate more charges. So I can actually think at this initial situation Q2 is smaller than, I'm sorry, Q2 is greater than Q1. That means charge on the second sphere is more. Now, if these two capacitors, spherical capacitors, are connected via a conducting wire, this is a conducting wire or conducting rod, whatever you say, conducting wire or rod or conducting rod. If you connect them via this conducting rod, what happens? You know, the charge will be redistributed. Charge will be redistributing among them. Okay, the charge will be redistributed among them, and you know, charge will flow in such a way that the potential of both are becoming equal. So this flow of charge will stop only when the potential of both the capacitors become same. So this is just like the flow of water or flow of liquid. Until and unless the height of the liquid became equal, the flow of liquid was continuing. Similarly, in this case also, charge flow will continue till their potential becomes equal. So this is the fundamental idea. And you know, here sometime you might be asked to calculate the common potential. What is the common potential? What is the common potential? Okay, what is the common potential? How do you find out the common potential? Suppose initially this guy has potential V1 and this has potential V2 on the surface. So as they are connected, the final will be V. But what is the potential? The idea is that, or the concept is that, the total charge is not going to be altered. So Q1 plus Q2 must be equal to Q1 prime plus Q2 prime, isn't it? This is conservation of charges. So charge is not going to change. Total charge is not going to change or alter. So in this case anyway, potential is same V. So I can write Q1 prime. Sorry, C1. Capacity also is not going to change. C1 plus C2 into V. This is the key total charge. Okay, total charge. And see here on the left hand side, I can write here this is C1 V1 plus C2 V2. That is equal to this. Okay, from here I can easily find out what is the V, capital V. V is the common potential. That is what we had to calculate. So C1 V1 plus C2 V2 divided by C1 plus C2. Okay, or this I could have written in this way also. Suppose the Q were given, then Q1 plus Q2 divided by C1 plus C2. This also is possible. If the informations are given like this, V1 and V2, initially they were like C1 and V1, initially C2 V2, then we can use this way. Or if the charges are given directly, then I can do like this also. Okay, Q1 plus Q2 divided by C1. That means the total charge divided by total capacitance. Okay, now how do you find out? Like, see, sometime this Q1 Q2 will be given. Okay, you will be first asked to find out. So V1 and V2 also will be given initially. So you have to find out the common potential. Then you might be asked to find out what is the charge now on this and this. So Q1 prime. So how to find out Q1 prime? You know, Q1 prime plus Q2 prime equal to Oh no, see Q, we have got already the common potential, so I can write C1 V common. So C1 is fine. What is V? V is the total charge, Q1 plus Q2 by total capacitance. So this is actually, yes. So this is the Q1 prime. Similarly, Q2 prime, how much we would get? Q2 Q2 prime will be again C2, the common potential V. So I can write C2 divided by C1 plus C2 into the total charge Q1 plus Q2. Okay, so this is how we can find out the new charges on the capacitors or the common potential. Obviously, the common potential is the one which you have to find out first. Then only you'll be able to find out the charges. All right. So now, once this charge distribution happens, then it is seen that there will be loss of potential energy. There will be loss of potential energy. But what is that loss? How much loss happens? How to find out that? How much is the loss? So how do you find out the loss of energy? So we'll just find out now. Loss of energy due to redistribution of charges. Okay. So initially, what is the potential energy? Suppose Ui. Ui will be how much? Half Q1 square by C, isn't it? So, or see, I'll write Q square by 2C, right? So initially the charges were separate, they were not connected by the metal conductor. So Q1 square by 2C 1 plus Q2 square by 2C2. Okay, so this is the initial potential energy. So what is the final potential energy? So we have to write here final potential energy, or let me write here, then we'll just do the we'll take the difference later. Okay, so what is the final potential energy? Now then it is Q1 prime square by 2C 1 plus Q2 prime square by 2C2, right? So these are the no, this is not the case. Or we can go with this also. Now it doesn't matter. If we just put the value of Q1 prime is equal to Q1 plus Q2 divided by C1 plus C2, that we can do, but that will be too much. So what we will do, we'll see when we are connecting them together. So what will be the total potential and what will be the total charge? Total charge will be Q1 plus Q2. So that is what we'll write here. Q1 plus Q2 whole square by 2 C1 plus C2. Okay, so this is actually final potential energy. Now we'll take the difference. Since it is said here loss, then the final energy must be less than initial energy, potential energy, that we'll see later. So delta U will be final minus U initial, sorry, U initial minus U final, because it is obvious that it will reduce or loss will happen. So see, I'm just putting these values Ui and Uf. So I'll just take half common, and then I'll write so Q1 square by C1 plus Q2 square by C2, then this part minus Q1 plus Q2 whole square divided by 2 C1 plus C2. Since I have taken half common, so C1 plus C2, this is only C1 plus C2 down. C1 plus C2. Okay. Now what I'll do, I'll take half common and see, we'll do the LCM part. See, LCM if we do, then we'll better to write it here, C1, C2 and whole into C1 plus C2. Okay. And now let us write the other terms. So it will be Q1 square C1 C2, okay, plus Q1 square C2 square C2 square plus Q2 square into C1 square plus Q2 square C1 into C2 minus Q1 square C1 into C2 minus Q2 square C1 into C2 C1 C2. Okay, so if we further simplify this, what will happen? So upon further simplifying, we'll get C1 C2 C1 square C2 square, say, okay, in the denominator C1 C2 C1 plus C2. Okay, so let us do further simplification. So we'll get like this, Q1 square divided by C1 square, then Q2 square divided by C2 square, then minus 2 Q1 Q2 divided by C1 C2. Okay, so okay, I'll just go to the next page. So delta U is becoming C1 C2 divided by 2 into C1 plus C2 Q1 square by C square plus Q2 square plus divided by C2 square minus 2 Q1 Q2 divided by C1 C2. This is what we'll get. See, up to this is also fine in terms of Q1 Q2 C1 C2. Or if the potential, individual potential was given initially, then see, suppose the conductor 1 has potential like surface potential V1 and this Q2 has potential V2, then we can write in terms of C1 C2 like V1 V2 also. See here I can write C1 C2, that is just like that. It will return like this, Q1 by C1, this will be V1 square, this will be plus V2 square, this will be 2 into V1 V2. So see, this is simplified to a very simple, like very nice form. This is V1 minus V2, V1 minus V2 whole square, V1 minus V2 whole square. Okay, so this is the thing. So C1 and C2, see here in this case, see why we were saying that this is loss. So C1, C2, these are positive, and also the quantity, this one, you look V1 minus V2 whole square are always positive, always positive. So these three quantities are always positive. Then what? Then delta U is also positive, and hence ui, initial potential energy, will be greater than the final potential energy. So this is what we get. Now suppose from this here, see, when there will be no loss of potential energy, at what condition? See, I'll write it here. So from here itself you look. So this is the expression. So from here, can we guess when this charge distribution redistribution will not happen, or loss of potential energy will not happen? So condition is this one: V1 is equal to V2. Then what will happen? If then delta U will be 0. That means initial potential energy and final potential energy will be same. So what does this mean? V1 is equal to V2 if the capacitors are at same potential, then there will be no charge flow at all. So there will be no charge flow if both are at the same potential. Even if they are connected via a conducting wire or conducting rod, there will be no flow of charge if both are at the same potential. V1 is equal to V2. In that case, this loss of potential energy will not happen. Okay, now today we'll start a little bit about parallel plate capacitor. So what is parallel plate capacitor? So if you have two identical conducting plate as you see here. So this is a conducting plate and this is another conducting plate. They are of same dimension, same size, same dimension. And if they are separated by a very small distance, then so these are two parallel conductors, identical conductors, and when they are separated by a very small distance, then they will actually constitute a parallel plate capacitor. Okay, and see, if you have two parallel conducting plates, and somehow you put some charges over here, some positive charges, obviously since this is a conductor, this will induce a equal negative charge at the same, see this space. Okay, this space. Okay, and if it is arched, then the negative charges will go. Anyway, this will actually constitute a parallel plate capacitor. Or if you have two conducting plates, see, if the conducting plates are connected via a battery, if it is connected to a battery, then see here positive charges, here negative charges will be induced. Okay, so this is actually parallel plate capacitor. So there are in parallel plate capacitor there are two identical conductors or conducting plate separated by a very small distance. That is actually parallel plate capacitor. Now, how do you calculate capacitance of a parallel plate capacitor? Capacitance of a parallel plate capacitor. How do you calculate? First of all, how to calculate capacitance? Capacitance we know Q by V. This is actually capacitance, isn't it? Q by V is capacitance. So we have to find out what is the potential difference uh, across this space between the parallel plate capacitor. So we know, suppose there is parallel plate capacitor. Each of these plates are having charges, magnitude of charge Q. capital Q. Okay, let me write here also capital Q. Capital Q. Suppose the area of cross section is A, then what will be the charge density here? The charge density will be plus sigma, say plus sigma, that is capital Q by A. Area of cross section is same for both the plates. So here also the surface charge density will be the same, minus Q by A. So these are surface charge density. Suppose this is air in between. So this air gap, actually this air also is a dielectric material or insulating material. So if you have infinitely long charge, infinitely long or infinite plane sheets, see, when I have these plates large enough compared to their separation, then we say these are infinitely charged or infinite charge plate. Okay, or infinite charge plate, we say infinite conducting plate. Okay, conducting plate. So we have already learned that if you have a conducting plate of some charge density sigma at any distance, so this is infinite plane sheet, so at any distance the electric field will be sigma by epsilon 0, sigma by epsilon 0. So suppose it is positive plate, so electric field lines will be going out from positive plates. Okay, and see, with the use of this, we can find out what is the potential in between, potential difference between them. How to find out? You have to find out what is the electric field at this region. This will be 0. We had already discussed. You can see at this region also will be 0. Only region is this part. The space between the conducting plate will have a uniform electric field, as you see here, and that will have, see, at this place, due to the positive, so this way it will be sigma by epsilon 0, and due to this negative plate also at this particular position it will go towards the negative plate, so that also will also have potential sigma by epsilon 0, sorry, electric field sigma by epsilon 0 at this particular position due to the negative charge. All right, so since both are actually directed in the same direction, so the total electric field inside will be sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. Okay, so this will be actually sigma by epsilon 0. So what is the electric field inside the plate, in the region inside the plate? Okay, that is sigma by epsilon 0. Electric field in the space between the plate will be sigma by epsilon 0. All right, so once we get electric field, see, we have got electric field between the plates. Then electric potential between the plates will be V is equal to E into D, right? E into D, electric field in that region into the distance between them, distance between the plate. Okay, and what is this E? E we have got sigma by epsilon 0, sigma by epsilon 0 into D, or sigma D by epsilon 0. This is the potential. Now what is the capacitance formula? Q by V. Q by V, let us write. So Q is capital Q here. Q by V. V is sigma by epsilon 0 into D. Okay, so this is potential V and this is Q. Q also we can write, like Q we can write sigma into A divided by sigma by epsilon 0 into D. So this sigma sigma will get cancelled and this epsilon 0 will go here. So this is sorry epsilon 0 A by D. So what is the capacitance we get? Capacitance value sigma A by D. Sorry, epsilon A by D. See what we get? Capacitance of a parallel plate capacitor. Parallel plate capacitor. So that is C is equal to epsilon 0 A so epsilon 0 A by D, you can see this A is the area of cross section and D is the dimension, like separation between the separation between the plates D. Okay, so this is actually the capacitance. Now we'll go to different situation. You can see this is also one way to charge the two conductors of a plate. See, somehow if you can put the charges on this arm, positive charges to this arm, and the other arm you are not giving anything but it is earthed, then the negative equal and opposite negative charge will automatically be induced. Okay, so we'll see few more important thing about this parallel plate capacitor. We'll see then effect of dielectrics. Effect of dielectrics. Effect of dielectrics. What does this mean? You know, in most of the capacitor, parallel plate capacitor, see these are two identical conducting plates, and in between there will be some dielectric medium. Okay, some dielectric, solid dielectric material will be inserted inside. Okay, inside or in the space between the plates. So why is it done so? Because see this is positive, this is minus q. Okay, so why is it done so? Because it serves, oh sorry, these are both positive, I have written, so this will be negative. See there are few advantages or few things this dielectric material can do. One thing is, see, upon insertion of dielectric material between the plates of the parallel plate capacitor, first problem is that first thing what it does is it solves. See, generally conductors, see these two conductors are given very high potential. So at very high potential, you know, very high in the sense electric field is of the order of 6 volt, 10 to the power 6 volt. That is actually the breakdown voltage of the air. Breakdown voltage of the air. Air is a good insulator, but see there will be breakdown of the insulator at nearly 10 to the power 6 uh, volt. Okay, potential difference across the plate. All right, so what it does is that It solves the problem of maintaining two large metal sheets at a very small separation without actual touch. So the conductor should not touch. In the parallel plate capacitor, conductor should not touch. But if I want to keep very large parallel plate capacitors or parallel plates, very large parallel plates, very large parallel plates at very small separation without touch, it becomes a little bit difficult. See, if I have a solid dielectric slab in between them, then it is easier to keep the conducting plates very near to each other without any actual contact. Okay, all right. So one purpose is done, and we can apply since it is not only air, we can apply large potential difference across this. Okay, we can actually, I'm sorry. Okay, so what happens, in case of dielectric slab, anyway, dielectric slab has greater breakdown voltage than the air. Okay, so this is actually dielectric. Suppose there is a dielectric, say, dielectric slab of dielectric constant K is inserted between two conducting plates. Okay, conducting plate. So when this plate of the capacitor is given positive charge, so this front part of the dielectric constant, dielectric material, this part will actually gain induced charges, so that will be minus, obviously. Okay, so that depends on sigma by epsilon 0. So at this place there will be some induction. Suppose this is minus q. Same thing here also. Suppose this is minus q. This plate is at minus q. So same positive charge plus q will be induced in this. See the field outside is E, and there will be some electric field inside the dielectric slab also. So the direction of that electric field is this. Okay, and original one has direction this way. Okay, so the overall potential, overall electric field in between the plates will be decreasing. How? Because of this insertion, the electric field will be and B will be so the dielectric slab does two things. One is actually without natural contact or actual contact, we can keep the metal surfaces, and maximum possibility of this conductance plates to be charged, as I said, beyond this breakdown voltage of air. This dielectric material of dielectric constant K can withstand. Okay, and we have seen the electric field. See how electric field you can see how can we do. See, electric field actually is sigma by epsilon 0. Here it will be epsilon 0 into k. Okay, we know epsilon 0, sigma by epsilon 0 is E 0. Suppose when this was only ER, electric field is E0. What is that? That is equal to sigma by epsilon 0. Now a dielectric material is inserted, right? So sigma by epsilon 0 into K. Okay. So this sigma by epsilon 0, this is E0, I have supposed. So you know this is actually E0 by K. This will be the, and K is actually greater than 1. Therefore the electric field we get after insertion of dielectric material is less than E0. Understand? So E0, that means when it was early, yeah. So all right, so we have seen how electric field is getting modified, that is E0 by K. Since K is greater than 1, so this is actually loss of electric field, or this electric field now inside the now electric field, effective electric field actually is less than the previous electric field. So when the effective electric field is known, then the potential, effective potential also will be known. Okay, so that will be E0 into D by K. E0 into D by K. E0 into D by K. So see E0 by, sorry, E0 into D, that is V0, right? So this is V0 by K. V is equal to V0 by K. This is how it is. All right. So once, see, this is, now look, now capacitor, capacitance of the capacitor when it is inserted with a dielectric material of dielectric constant K, then say we know Q, C is equal to Q by V. Q by V. Here capital Q by V, anyway that could be written as sigma into A. V we have already got, that is actually V0 by K. So V0 by K. So V0 by K, here it is actually sigma so Q is sigma into A, and here it is epsilon 0, epsilon 0, sorry, sigma by K epsilon 0. Okay, so you know this will be epsilon 0 A, obviously there will be D vector here. This is electric field into D. K epsilon 0 into A by D. That means you know this is epsilon 0 A by D into K. So this is C0 when we measure the capacitance in AR. Okay, so it is, see, you can see that the capacitance is actually increased by a factor K times. Okay, K times. Okay, we can increase the value of the capacitance to a very large extent by insertion of dielectric material in between the plates. Okay, so we'll stop it here for today. We'll take up this topic again in the next class and discuss various type of this insertion of dielectric material, or we'll just take one more topic here. Let me just go for one more part of it. Suppose, okay, so suppose parallel plate capacitor filled with partially filled partially filled with partially filled with dielectric material. Okay, so figure is something like this. So these are two parallel plate capacitor, and suppose there is a dielectric material of thickness T. This has thickness T, and this thickness is, or separation is, D total. So this is a dielectric material of suppose K. Okay, and the rest of the thing is air. All right. Now, what will be the capacitance of this? Okay, what will be the capacitance? So let us say that is C1 or C prime, whatever, and C0 is in air. So you know what we have to do? We have to the same fundamental idea. C1 has to be total, the charge by V. So this potential is important. Okay. See, any of this can be written as sigma into A, but this potential, this we have to find out. So what will be the potential? See, for the air, we know the electric field for the air will be sigma by epsilon 0, that is for shear. This is the electric field. Okay, so this is in air. So then potential difference V air will be E air, this is in air, E air, or E0, this is E0, and this is V0, say. So V0 is E0 into the separation is now D minus T. This is fine. Okay, and this E0 can be, I think I should write it, E0 sigma by epsilon 0 D minus this one. Okay, now within this material, what will be the potential? That is, suppose V. V will be actually E into T. What is this E? E will be again E0 by K into T. This is the thing. E0 is what? E0 is again sigma by epsilon 0, then T by K. So this is the thing. So I have got two potential, right? So total charge is sigma into A. So capacitance sigma into A divided by V1 plus V2. See, this is V plus V0 plus V. Sorry, V0 plus V. V is within the across this. V is across the dielectric material. V0 is across the air. So sigma into A divided by. See, V0 is sigma by epsilon 0 into D minus T. Okay, and this is sigma by epsilon 0 into T by K. See, this is sigma by epsilon 0. This sigma, if I take common from both sides, epsilon 0 anyway. Let me just write it. So this sigma goes off. If I take common, so A divided by, see, d minus t over epsilon 0 plus t by k epsilon 0. K epsilon 0. Okay, I'll just go to the next page and write. So C1 will be then sigma we have already cancelled out. A divided by d minus t, this is in the air, plus t by k epsilon 0. Epsilon 0, if we take it to here, epsilon 0 a, multiply epsilon 0, then d minus t plus t by k. Okay, so this is the formula for the partially filled capacitor, parallel plate capacitor. Okay, so if you have, see, if you have rather than one, if you have more than one, so what this is actually a formula when, so the capacitance of a parallel plate capacitor, when the parallel plate capacitor is partially filled with the dielectric material of dielectric constant K with thickness T. If this is the situation, then this is the formula epsilon 0 A divided by d minus t plus t by k. If there are many, for multiple number of, see, the same formula can be extended if more than one, if more than one slab, sorry, more than one slab of dielectric constants, dielectric materials, okay, more than one slab of dielectric material, one slab of dielectric, more than one slab of dielectric material are are placed in between the plates, then the same formula or for capacitance will be, so sigma into epsilon 0, this will be all right. So there here, see, suppose I have n number of see, I have, suppose this are, see, I have n number of such slabs of thickness T1, T2, Tn. Okay, and the separation is D anyway. This total separation is D, and I have taken n number of such thin dielectric slabs. Okay, so then here it will be D minus T1 minus T2 minus of Tn. Okay, so this is here, and again plus here T1 by K1 plus T2 by K2 plus T3 by K3 plus dot. Okay, so this is the formula for more than one dielectric slab. Okay, okay, in the previous equation, see, in this case, if the thickness is totally filled with, if T becomes D, then what will happen? The total space is filled with the dielectric material itself, then epsilon 0 A by T by K. That means K epsilon 0 A by uh, okay. Uh, all right. So if suppose here it is D, say D. If suppose this space between the conducting plates are filled with conducting material. In case of conducting material, this K is 0. Sorry, K is infinite. For conducting slab, K is infinite. K is infinite meaning T by infinite. That means this term will go away. So we'll get this minus T. Alright, so when this is conducting slab, conducting slab. Okay. Alright, we'll stop it here for today. Next day we'll take up further. Alright, so thank you for your patience. Bye for today.